replacing the two exponential terms by a sine and cosine functions, I would have e to the power negative zeta omega n, a cosine omega n square root of 1 minus zeta squared t plus b sine omega n square root of minus 1 minus zeta squared t now I can convert or combine these two sine and cosine terms into one sine function e to the power negative zeta omega n t sine omega n square root of 1 minus zeta squared t plus some phase angle, and the amplitude will go back to the amplitude of the motion x. So now the term multiplying t in the harmonic function sine, as we said when we discussed harmonic motion, this term will be the frequency of the response. So the frequency is slightly different now in this case than the natural frequency because of the addition of the damping term here. So I will call this the damped frequency. Omega d equals omega n 1 minus zeta squared, and I will call this damped frequency. Okay. So x of t can be simplified as x e to the power negative zeta omega n t sine omega d t plus phase angle phi. Now I can expand this sine term, the sum of two angles, as x negative zeta omega n t sine, the sum of two angles, sine omega d t cosine phi plus cosine omega d t sine phi. Now let's compare these two forms. This form of x of t to the original form here. We will notice that A is the coefficient multiplying the cosine omega d t, which is in this case, here's the cosine, so A will be the sine times x. So A will be sine phi multiplied by x and B is the term or the coefficient multiplying the sine omega dt. It's multiplying the sine here is the cosine phi times x, so this is x cosine phi. Now I can find the relationship between A and B, x and phi. If I square A and B and add them together, x will be the square root of a squared plus b squared, and dividing a by b, x cancel, a by b, I will have sine phi divided by cosine phi, which is the tangent of the phase angle phi. So now I have these two relations that I can move from one form of x of t, which is the sum of two sines of sinusoidal functions, cosine and sine, to this form, which is just one sinusoidal function with a phase angle. So now x of t is some amplitude x e to the power negative zeta omega n sine omega d. Now this is a sine function. Now the amplitude of this sine is this term. This is the amplitude of the sine wave. The sine wave is normally, the amplitude of the sine wave is plus minus 1, and this is multiplied by this term. This term decays to 0 with time, e to the power negative value. So if I plot the amplitude only of the sine wave, it would be some envelope that approaches 0 with time. And this is the boundary of the sine wave. So the response, sine multiplied by this amplitude, will look like a sine wave, but with amplitude decaying with time. So the response is sinusoidal response, but its amplitude decays with time, and this is for zeta less than 1. And we call this the underdamped system. And this is the important part or interesting part for us in the vibration course, because the other cases, the response is exponentially dying to 0, and there's no vibration in the system. So this is the case where I will be studying most of the vibration analysis, where zeta is less than 1. Now, what if zeta is 0? Zeta is 0, and recall that zeta is c divided by c critical. When zeta is 0, that means that c is 0. That means I don't have any damping in the system, and this means the system is undamped. And when the system is undamped, when c is 0, zeta is 0. Okay. We go back to this equation. E to the power 0 is 1, so I will have x times 1 sine. When zeta is 0, we call that omega d is omega n, square root of 1 minus zeta squared. So for zeta 0, omega d will be omega n t plus phi. And this is exactly the response we derived in the case of undamped systems. So the undamped system is basically a special case of the damped system response. And in this case, it's a sine wave, but the amplitude is constant, so the response will be a sinusoidal response that continues forever. And these are the different types of responses that we expect for different values of the damping ratio zeta. Now, let me also try to derive or find the values of the constants x and phi, or a and b in the other form, which are to be determined by the initial conditions. So if I go back to x of t, the form equals e to negative zeta omega n t, a cosine omega d t plus b sine omega d t. The derivative of this function x dot of t, need to find the derivative because I would have to substitute two initial conditions, x of 0 and x dot of 0. The derivative of this function is basically the multiplication of two functions, so I will have to use the chain rule. The derivative of the first term is negative zeta omega n e to negative zeta omega n t, multiplying the same function omega d t plus b sine omega d t, and then plus the first function e to negative zeta omega n t, and the derivative of this term. The derivative of cosine is negative omega d a sine omega d t. Derivative of sine is cosine plus omega d b cosine omega d t. Now I will substitute the initial conditions. Let's assume initial conditions x of 0 is x0 and x dot of 0 is v0. So substitute x, or time t equals 0 in x of t. X of 0 equals e to the power 0 is 1, cosine 0 is 1, sine 0 is 0, so I will have only a. And substituting t equals 0 in x dot of t, I have x dot of 0 equals e to the power 0 is 1, so I will end up with negative zeta omega n, negative zeta omega n, times cosine 0 is 1, sine 0 is 0, so it will be just a plus e to the power 0 is 1, sine 0 is 0, and I will have plus b omega d. And this is equal to v0, and this is x0. So if I substitute the value of a here and solve for b, I will find out that b is zeta omega n x0 plus V0 divided by omega d. So now I have A and B for initial conditions x0 and v0, and also I can convert from A and B to x and v using the relations that we found earlier, which were x equals square root of a squared plus b squared, and tangent of phi is a divided by b. So I can use either constants to find the values of the coefficients of the response based on the given initial conditions. So I can use either this form or the form with the sine and cosine terms.